Okay, in this problem we have a square ABCD and as a side length of 3, and we choose a point P alongside AD such that AP is 1, so then PD is 2, and then we choose a point Q along PB such that it maximizes DQC. So let's think about the angle DQC. So let's think about how this would work. So it's kind of hard to wrap our minds around angles. So let's think about this nice fact. So if we had to find all points R, maybe all points R, such that DRC is a particular angle, let's just say X degrees, um, then we could all the points DRC that all the points R that satisfy this would lie along a circular arc that passes through points D and C. So I meant to draw this arc so that R lied on it. And then so we can see all angles here are the same, and the reason for this is because I don't know, because of symmetry there. And so we can use this fact, and also the fact that the larger our arc is, so like this is a larger arc. Wait, I should draw this in a different color. So the larger our arc is, um the smaller the angle is that also. So this angle, this green angle is smaller than either of the red angles I drew. And the fact that this arc doesn't intersect with side PB means that there's no point with this. There's no point with this angle, at the DQ. If we choose this point R, DRC, there's no point R along side PB such that DRC is that angle because there's no intersection. So if we draw an even bigger one, like maybe this one, you can see we get an intersection. And this intersection means that there is a angle. So this angle is possible. So there's a point along PB such that DRC is that angle. So the bigger arc means a smaller angle, and the problem asks us to maximize the angle, which means we want the smallest circle possible passing through points D and C that intersects with line PB. And to do this, we're going to want the circle to be tangent to PB. So let's draw what we want our circle to look like. Oh, shoot. I thought I was drawing circles. Okay. Um, so, oh no. Okay, there. So this is kind of what we want our circle to look like. And so we can see that all points on this arc, have the same angle measure. And we don't need to find this angle measure, but we need to find where Q is. So now this question is no longer about angles, but it's about a circle. So the question is, if we have a circle that's passing through points D and C and tangent to PB, it has a point of tangency with PB, so we'll call it Q. How far apart are P and Q? This is a pretty difficult problem in itself, and there's something very clever we can do. It's not chord bashing, although chord bashing is very, very clever. But chord bashing takes a long time and a lot of math skill, which I don't have. So we're going to do it the easy way. So we have a lot of chords. Well, actually, no, we only have one chord, DC. DC is a chord of the circle. And we also have a tangent. So the words chord and tangent incite the thought of power of a point. So that's what we're going to do. So we're going to extend segments BP and CD to meet at a point. We'll call it R. And now we'll use power of a point on R. And this turns out to work. So we have that DC is 3, and because of similar triangle ratios, because this is a right angle and this is a right angle, since we're just extending DC, that's all we're doing. So then RD is going to be 6. And so therefore, we can do power on R, like I said. So we have that RQ squared is equal to RD times RC by power of a point. And now we know what RD and RC are, so that's 6 times 9, which is 54. So therefore, RQ is root 54. And by Pythagorean theorem, we have that RP is equal to RD squared add PD squared, which is 36 squared, 36 plus 4, which is 40. So therefore, RP is root 40. And if we look at our diagram, we can see that PQ is just RQ minus RP. And we already know what those are. That's root 54 minus root 40. And our problem asks for this. So we found that it's root 54 minus root 40. And it asks for the sum n plus n. And that's 54 plus 40, which is 94. That's C, and we're done.